This is a very, very important figure right here to understand. We've seen this before. Here in the past, what I've been using is Nu for a nucleophile. It's got lone pair electrons. Usually, or many times, is negatively charged, but it doesn't have to be. Okay, so we'll find out later on. Like for example, and then you have some type of, in this instance, a metal cation. Almost always for us, these are the biggies that you see used the most often. We're going to be talking about potassium, sodium. What's another one you suppose? It's along the same family there. Lithium. Whoops, that's supposed to be an Li. You can have magnesium or calcium, one of the others, but remember that's a 2+, and so then you would have 2 of the Y minuses. And I apologize if I use Y sometimes, or if I use Nu for nucleophile. It means the same thing here. Okay. It just means I like using Nu because that way you get used to seeing it as a nucleophile. And sometimes the book uses it Nu, at least in the old editions, and sometimes they like to use that generic Y. Now, once in a while, later on, I'm kind of skipping ahead, is we can also imagine, like, what happens if we see this? It's the same principle, okay? So I wanted to point it out because here we have an atom that's got lone pair electrons, so it could be nucleophile, but we don't have a cation. It's not lithium, potassium, or sodium, it's hydrogen. And so then you can imagine in the final product here, this would be a hydrogen halide, and then the Y, which would be the oxygen, would be attached to the R group. Okay, that's why I just wanted to point out it's not 100% of the time that you'll see sodium, lithium, or magnesium there. You could have a hydrogen. It's just that here, this is methanol. The hydrogen is not detached. It is attached. Okay. All right, so this, I would want you to know this mechanism. It should be fairly simple by now. You see a Y. If this is this mechanism right here, is this a Sn1 or an Sn2 reaction, the way they have it written out? An Sn1 or Sn2, where we have a nucleophile coming, smacking the delta plus of the carbon with an X leaving. It's an Sn2, because as one comes in, the other one's leaving. Every time, and hopefully you should start to understand this, the Sn1, you have to form the carbocation. Okay, because that's where the water, in the instant before, we talked about the water left to leave the carbocation, which then comes in and gets attacked. Remember, then we had a 50-50 shot, essentially, assuming that wasn't too big and bulky group on one side, is a 50-50 shot of it being attacked from the front or the back. Here, it's always a backside attack. Then you have the product, where the nucleophile is now attached to the carbon, and you have whatever, metal halide. Also, later on, I want you to get used to the fact that many times in the book, and especially in biochemistry, you do this all the time, they don't even write, because if you think back to Gen Chem, this is called spectator ion. The M plus itself doesn't do anything. So sometimes they don't even include it. Okay, and so just because it's a spectator ion. But this is, in the beginning, a lot of times you try to show it. So why did I go through all that spiel? First of all, I guess we could also review this. So for Sn1, you always, because every single time that you have an acid, you protonate. And versus Sn1 or Sn2, it's the same first step. And it's fast, it's reversible. You get this alkyl oxonium ion, which is just a fancy word. Alkyl means it's got an R group on it. This is an oxonium ion. Sn1, the water leaves first to make the carbocation, and then quickly the X, because so far we've only seen halogens be a nucleophile, the X would come in and smack the carbocation to make your alkyl halide. In Sn2 reactions, from the alkyl oxonium ion, you have this coming in for a backside attack as the water was leaving to make your alkyl halide. Okay, so this was called a nucleophile because it had the lone pair electrons that came in and attacked. The water here is called the leaving group because it left. Okay. So, and pseudo-halides, as I say, can also act like leaving groups, okay? Which I already mentioned that just 5 minutes ago or less. So, why am I going with this? Here we go. Now, we can actually use these mechanisms, whether S1 or S2, can be used for a whole host of nucleophiles. Okay? So almost always, so I have written this down somewhere, almost always, M plus is going to equal something like potassium, lithium, or sodium. But don't be alarmed if later on you start seeing hydrogen on there. And then we just have our nucleophile. Okay? We can either call it, here in fact I'll specifically write it out this way. Nu minus is the same thing as Y minus. That's just a nucleophile. Nucleophile. Okay. So now I'm going to just write out a bunch of different possibilities here. I think I'm even going to add one that your book doesn't have, just because in vivo and biology and biochemistry, it's so important. It's this one. That's supposed to be an S. Once again, the M, if I wanted to, if you want to, you can even give specific examples for one of these. Maybe I'll do one in a moment because I don't want to for every single one of these for time's sake. So this first one, of course, the M is a metal cation, but what does that look an awful lot like? MOR looks an awful lot like, if the M was a hydrogen, it would be, if the M was a hydrogen, it's an alcohol. Well, when an alcohol loses its hydrogens, then we know what it's called, because it becomes negatively charged. Because remember, this way is the exact same thing as saying the following. Here, let me just write it out. Remember, that is just a cation, that's the spectator ion. It really looks like this. Those are lone pair electrons. It really looks like that. So it's no longer an alcohol, because what are the endings, like the suffixes from Gen Chem if something is negatively charged? You only learn like 2 or 3 of them. Think about it, like when a sodium cation forms with a chlorine anion, what's that called? NaCl is sodium chloride. So ide is one of the endings. But does anyone know what's one of the other endings? 8 is the other. Those are the 2 biggies. Ide and 8. ITE is also like sulfite and phosphite and some of those. But ide and 8 are the 2 biggies. This goes from becoming an alcohol to an alkoxide. Okay, so that's why it's the IDE ending. So for example, if we had something like a very specific one, I'll just draw it up here, because I probably won't do this for every single one. They may draw it like that. But remember, the K is just a spectator ion. It's not covalently attached to there. It's just going along. And just like we say sodium chloride, this would be potassium methoxide. Okay? Methoxide and ethoxide are the ones that we see a lot of, especially ethoxide. But you could have pretty much any of them. Now, I wanted to do this because now I'm going to just do a generic reaction every time now. So let's say that we started off with this. Or I'll go ahead, I'll give us an example. Let's say we have that potassium methoxide plus, and now we're going to start using halogens instead of alcohols, because the alcohol itself is not a great leaving group, whereas a halogen, it is. So let's start using it. Let's say that we do it with iodomethane. Oh, sorry, I didn't mean to do that. So for those who had me for Gen Chem, these are the kind of reactions that almost, I call them like, they were like swapping partners. So they were the swingers reaction. Technically it's a metathesis kind of thing, because it's a substitution reaction. But if we look over here, and I don't want to have to take as long for all these, we have a potassium, which is a spectator ion. We have the methoxide, and we have iodomethane. What do we have over here that can be the nucleophile? That would be the generic Y. Like, what part of this is the Y? The oxygen. Okay, so that's why if you needed to, just imagine this really is K-O, oh, whoops, I said K-O-Y, K-Y, and it's K-Y, okay, or M and a Y. So we know the oxygen's doing the attacking. On this other side, what here is going to be attacked? The carbon, the hydrogen, the iodine. And so this is where we draw it out. And I won't draw it out for every single one of these, but I draw it out like this. Oops, I don't know how I accidentally hit it and changed colors. That hydrogen is not supposed to necessarily be a different color. So what will be attacked? The carbon, hydrogen, and iodine. So we have this oxygen coming, and it's going to be smacking something over here. And whenever it smacks, something has to leave, because that you can't have, the hydrogen can't have 2 bonds, the iodine can't have 2 bonds, and the carbon can't have 5 bonds. So something has to leave. What do we have over here that's a good leaving group? Is it going to be a hydrogen that has to leave with electrons? Is it going to be the carbon that leaves with electrons? Or is it going to be the iodine that leaves with electrons? Iodine. Okay, halogens are a good leaving group. I've said that multiple times now. Hopefully it starts to sink in. So the mechanism is really simple here. Boom. Boom. And so now, in this instance, we would actually be left with okay. Or if I wanted to draw it in the, there we go. That's the same thing. This is using the little stick method. So we went from an alkoxide, or here, technically we went from an alkyl halide. What kind of compound? You should know your functional groups by now. What functional group did we just make? ROR is ether. So now we know a way to make ethers. So we can now go from an alkyl halide to an ether. You just have to have a substitution reaction using an alkoxide. This N3 is called azide. Oh, stop doing that. That's azide. So this is a metal azide. So you could have lithium azide or sodium or potassium. It doesn't really matter. This is an azide. So I'm just going to do a reaction here. And this is what it looks like. Because if you don't remember from Gen Chem, from doing hopefully by now you'd be able to sit down and figure out the Lewis structure, but this is what it looks like. 2, 4, 6, 8. Okay, that's what it looks like if you draw it out. This one hopefully is fairly simple. So if we look at the Mn3, which part of that's going to be the Y? The what? The N3, okay? Because on this one, doesn't matter what the M's are. You just look to see where we have the lone pair electrons. And on this one, where's the lone pair electron? Pardon? It's the N3. It's one of the terminal nitrogens, okay? So that's why now we can just literally go and we could have something. I'll do lithium. It doesn't really matter. No, whoops. Plus this way we can actually form an azo compound. Oops, that's supposed to be 6. Okay. Plus the inorganic, by the way, I didn't put the first one on there, but the inorganic compound product on the first one would be potassium iodide. A lot of times we don't even show it. The second one would be lithium chloride. So now we have a way to add an N3 group on, which we're going to find out later on is a really good leaving group in and of itself. Does anyone remember what CN? This is one that you were supposed to memorize. It was one of the, remember you had to remember like some polyatomic anions like sulfate and phosphate, and there's one called CN. It's cyanide. Okay. And cyanide looks like this. Excuse me. It's a triple bond. The carbon has a formal negative charge. So what part of that's going to be the nucleophile? Carbon and a nitrogen. What's going to be doing the attacking there? The carbon. And so if we did in a specific example, let's see what one haven't we used. Sodium. So we'll do sodium cyanide. Please don't take sodium cyanide. It's a poison. And we put it with, oh, it doesn't really matter. I'll give you a moment to write out the product. So once again, this is the M, this is the Y, or the NU if you want to do it as NU. So how many carbons are going to be in the final product here? In the organic product, I should say. There are 6. I know that's kind of a trick question because a lot of times I get people who say there are 5, but they forget that the nucleophile itself is a carbon. So there are 6. 1, 2, 3, 4, 5, 6. So now we went from an alkyl halide, because this is an alkyl halide. What functional group do we make here? It's a nitrile. So hopefully you're starting to see a pattern here. So if we look at MSH, which one of those, which M, the S, or the H is going to be the nucleophile, the Y, that goes and does the attacking? The S. By the way, this one is called a hydrogen sulfide, so like lithium hydrogen sulfide. It's a lot like hydroxide, except that it looks like this. I mean, it looks an awful lot like hydroxide. So if we do one of these as examples, there's bromoethane. I'll give you a moment to write out the final product. So how many carbons are in this product? 2. And then we have the SH. And so we went from an alkyl halide to what kind of compound? Oh, this is a thiol. You guys just sound so motivated now. Okay, then we have this next one. I don't know if you recognize or understand know what kind of compound that is right there. It's called a carboxylate because it looks an awful lot like what functional group that you had to memorize. The carboxylic acid, which, except the M is a hydrogen. Okay, and so what happens is whenever the acid loses hydrogen, it's called a carboxylate. What part of that is going to be the nucleophile that does the attacking? What's the oxygen? By the way, that right there is potassium acetate. It's also called potassium ethanoate, but most people call it acetate. And I'll give you a moment to write out the final product or products. Okay, so now when we write this out, this is what it's going to look like. We have the benzene ring, we have 1 carbon, oxygen, carbonyl, and another carbon. And so what kind of compound did we make now? We went from an alkyl halide to what kind of compound did we make? You need to know the functional groups. This is ester. Awesome. You get the metaphorical cookie award today. This is ester because we have R, so that just means a carbon, O, acyl or carbonyl group, and then R. And so it's an ester. This one, well, I'm not going to give you the name, give it away right here. But here we have MSR. Which one of these, which letter is going to be the nucleophile that goes and does the attacking there? It's the S. It's very similar to the thiol that the thiol that we made before, the hydrogen sulfide, I should say. And so, if I give a specific example, what one have we used? Let's see, sodium. There we go. I'm going to put it down here, down a little bit lower. give you a moment to write out the product or products. So we have, let's see, 1, 2, 3, 4, 1, 2, 3, 4, sulfur, 1, 2, 3, 4. Oh, I made it nice and 1, 2, 3, 4, symmetrical. So what kind of compound did we make here? What's this one right here? It's not a thiol, but it is a sulfide. Okay. All right. So now we've already learned a lot. We've learned how to go from alkyl halides, all of these were alkyl halides, and convert them using substitution reactions. And we'll talk about whether it goes Sn1 or Sn2 later. Convert them into a whole host of things. Okay. So now we can make ethers, we can make azo-containing groups, nitrile, thiols, esters, sulfides. You can see that same thing over and over and over again. There are a couple things I just want to point out. I want to point out that nucleophilicity, which to me always sounded like a great name for a punk rock band, nucleophilicity. It's related to basicity, okay? And since they are technically Lewis bases, they have electrons that go out and do the attacking. We've already discussed all this, how the fact that it's got to be halogen, and it's the carbon that's directly attached to the halogen that gets attacked. Okay, this is called a leaving group. One thing I want to point out is the carbon that gets attacked has to be sp3 hybridized. It's got to be tetrahedral. It cannot be an alkene, and it cannot be a benzene, like an arene. Okay, arene, not arene, arene. Okay, but alkyl halides or pseudo halides. So you can have a sulfonate like what we've done towards the end. That's why I wanted to touch upon it briefly this class at the beginning of the class. That they are both great leaving groups. Okay. And some people, let's see, how can I explain this? Some people get this messed up. If you remember, the best nucleophile, because remember, halogen can go in and do the attacking. Which is the best nucleophile? Was it, now this is, let's see, oh, I hate the way that this one's set up. Whenever we had the alcohol, whenever it looked like this, and we had the halogen, the halide that would come in to do the attacking, to pop this off. Which halogen was that, fluorine or iodine? That was the best one at doing the attacking. Do you remember? It's iodine. Okay, iodine is the best nucleophile. It's big, it's huge, it can go out there, it can do the attacking. But now, also when we think about what happens whenever the alkyl halide itself is getting attacked, iodine is also the best leaving group. Okay, I don't like the way they said this is most reactive. I like talking about leaving groups. And the reason why is iodine by itself, I-, remember it was the most polarizable. It's the big blobby, the jiggle factor. It's perfectly happy by itself. It's the strongest acid. When it's HI, it's the strongest acid. This is the strongest bond. That carbon-fluorine bond, remember fluorine's really tiny. It holds on to its electrons. It doesn't like to leave. Okay, it's perfectly fine. It's a little tiny thing. Doesn't want to pop off easily. Iodine's big and blobby. It can pop off because that bond between the nucleus of the iodine to the nucleus of the carbon is the furthest one apart. And so the best leaving group is also the best nucleophile. And we're going to see that over and over again. In biochemistry, we talk about it all the time because sulfur is a better leaving group than oxygen, but it's also a much better nucleophile as well. So our body that uses this to its advantage all the time. So we utilize sulfur a lot more in those kind of transfer reactions than we do in oxygen, because an oxygen just isn't as reactive in that sense. Okay. All right, so I'm going to go ahead and I'll end class with prayer.